Yeah, in the last video we introduced the concept behind boosting, and in particular we talked about the AdaBoost algorithm, adaptive boosting. And in this video we are going to talk about a more modern version of boosting called gradient boosting. And the term gradient, it relates to gradient descent. If you heard of gradient descent, for instance, the students who took 453 last semester in deep learning, we used a lot of gradient descent for training neural networks. Here the concept is kind of similar, like minimizing functions with gradient descent like update. However, we are going to use decision trees for that. So there's an interesting idea of using gradients to combine different decision trees into a boosting model. Yeah, I should also say gradient boosting is among the most widely used machine learning algorithms for working with tabular data sets. It's very popular in especially competitions like Kaggle. A lot of competitions have been won with gradient boosting. So what is gradient boosting and how does it work? Yeah, like I mentioned before, gradient boosting is somewhat similar to AdaBoost. So it's still a boosting algorithm, which means we have a sequential process. So we fit models iteratively in a sequence, and we can use decision trees for that also. So if we use decision trees, these trees are fit sequentially to improve the error of the previous round or the previous tree in the sequence, in the boosting sequence. And effectively we are boosting weak learners to become a strong learner, to a strong model. And that is what it has in common with AdaBoost, or the general boosting framework. And because boosting in general is a sequential process, so gradient boosting is also a sequential algorithm. In contrast to other types of ensemble methods like bagging, the challenge here is also that it is hard to parallelize. We will briefly introduce some newer approaches to gradient boosting that try to do that, the parallelization, to make it more efficient. But in general, boosting algorithms such as AdaBoost or gradient boosting are harder to parallelize compared to other ensemble methods such as bagging or random forests, which we will be discussing in the next video. And in addition to the similarities to AdaBoost, also briefly about the differences. So what's different in gradient boosting compared to AdaBoost is mainly the way how the decision trees are fit. So the way we are fitting them is different from AdaBoost. Here in gradient boosting, for example, we don't have weights for the misclassified examples. So gradient boosting doesn't use weights for the training examples, for the examples, but also there are no weights for the classifiers. There is a way that we weight the predictions, but there is no explicit classifier weight. And instead of, for example, using majority voting, we are adding these different predictions, as we will see shortly when I introduce the basic concept how gradient boosting works with an example. So the key idea also for the gradient boosting is that we have a differentiable loss function. So for this loss function we can compute the gradient then. That's where the name gradient, or the gradient term in gradient boosting, comes from. And usually also, where in AdaBoost we usually use decision tree stumps, in gradient boosting we don't use the stumps. We usually use just the tree root node in the first iteration, and then we use deeper trees in the consequent iterations. Computer scientists like powers of 2, so usually the decision tree depth is a hyperparameter that has to be chosen, but usually people use something like a maximum depth of 8 or 32 and stuff like that. But we will see in a few moments how gradient boosting works with an example, and then this will become more clear how the decision trees are used in gradient boosting. So the conceptual overview of gradient boosting is outlined here. I try to keep it short in 3 basic steps. So the first step is constructing a base tree. So base means like very like basic tree basically. So it's just the root node. So we said before a decision tree stump is a decision tree with one split. However, in the base tree, in the root node, it's just this root, it doesn't split at all. So we are just using the root node to begin with. And then based on the predictions of the root node, for example in regression, it's just the averaging, the average target label at that node. Then we build the next tree in the next iteration based on the prediction error of the previous tree. So we are building a new tree based on the error of the root node. And in step 3, we then combine the trees from step 1 and step 2 and then go back to step 2. So we repeat this process multiple times. So every time we make a prediction, we compute the error of the prediction, and then in the next round we fit a tree based on this predicted error. And also when we do that, when we make, well, every time we add a new tree, we combine the trees, so the prediction is always a combination of the prediction of the previous trees. And this looks very simple here. It's actually also not very complicated, but maybe it takes some time to wrap your head around the concept that now we are fitting trees on the errors in the consequent rounds. So in the following slides I will walk through an example to illustrate how that works on a very, very simple data set. And we are only talking about regression here because it's conceptually a little bit simpler. But the same concept applies for classification too. For classification though, we haven't talked about logistic regression yet, and I'm not sure how many are familiar with logistic regression. It's a topic that we cover in Statistics 453 in the deep learning class. But I'm pretty sure most of you are familiar with linear regression, so in that case it's a little bit easier to illustrate gradient boosting in a regression context where we also use the mean squared error as the differentiable loss function, similar to linear regression. However, the same concept applies also to classification. We would, for example, use the negative log likelihood loss instead of the mean squared error. But yeah, let's just get started and talk through this regression example, and I think then everything will become more clear. So here I made this simple data set. This is not really based on real data, it was just, I would say, an educated guess. So what we have here is like a house price prediction problem where the price is in million of US dollars. So we have 3 variables here, 3 features. 1 is the number of rooms, 2 is the city, the location, and 3 is the age of the house. And let's say in Boston, if we have a house with 5 rooms that is 30 years old, it would cost $1.5 million. In Madison, 10 rooms, 20 years old, it would cost $500,000. I'm not sure, I think this is approximately realistic, but yeah, it's just like a toy data set, of course, right? So then I have the cheaper houses even in Lansing and even cheaper in Warneke. And so recall, step 1 is constructing the base tree, so constructing the root node. So the root node in a regression context, so here again, this is like a regression problem, and the task is predicting the target here. This is our target, and this whole thing is our training set. So when we start with a root node, or in general when we have a decision tree and we make a prediction, so it doesn't matter whether it's the root node or not, if we have a decision tree like that, and we go down here to this node and there are multiple examples at that node, the prediction is based on the average at that node. Right now we only have the root node, so the root node consists of all the 4 houses in the training set, right? Because the root node doesn't split anything, so the houses, the prices are 1.5, 0.5, 0.25 and 0.1, so it's this target variable here. And for this root node here, the average is 0.5875. So that would be the prediction to start with. So for every data point, the root node would predict 0.5875. Of course, this is not a very great prediction. It's depending on which training example we look at, it's either better or worse. For example, it's not far away from 0.5, so for medicine, the prediction wouldn't be that bad. For other cases like Warneke or especially Boston, the prediction would be pretty bad. But yeah, and on average, this is the best prediction in terms of minimizing the mean squared error if we just use one node. And now let's go to the second step where we build another tree based on the errors. So in step 2 we said we built the next tree based on the errors of the previous tree. So here we are first looking at something called the pseudo-residuals. Residuals can be computed in different ways, and there's a special meaning for that in the context of linear regression, for example. So here we are just calling them pseudo-residuals. How we arrive at the pseudo-residual term we will discuss later after walking through this example. Right now, consider the simple case of the pseudo-residuals as the difference between the true label and the predicted label. So the residual is computed as the difference between the true label and the predicted label. So we are subtracting the true label and the predicted label, where this is the prediction by our root node. It's always the same, right? 0.5875. And when we subtract the true and predicted label, we get these residuals for each case, for each training example. And we can also think of them as our errors for now. So just to recap again, we built the next tree based on these errors of the previous tree. So now we are actually considering these residuals as our target for the next tree. So for now, just pretend this is your new target variable, your new y. Instead of fitting a tree on y, we are ignoring this now. We are only focusing on R1, which is kind of like our new target variable, and then we fit our tree on this variable. So here I sketched out how a tree may look like. So for instance, consider the first training example. So for the first training example, we have an age greater or equal to 30, right? So this is true. So it's a yes, and this would be then basically the Boston data point. For the second case, we don't have an age greater than 30, so it's a no. And then we check the number of rooms equal or greater than 10, that's a yes. So medicine would go here. And because the other ones we can also just write that down, they are all younger than 30 years old. I mean, the houses are newer than 30 years old. So let's put also Lansing and Warneke at this node here. And then we check for the number of rooms. Like I said before, medicine has greater than 10 rooms, so this case would be medicine. And the other ones, 0.33, this would be Lansing, and the last one would be Warneke. So let me write Lansing and Warneke here. And in decision trees, if we have multiple training examples at a given node, we take the average. So this is the average of these two values here, and that is how our decision tree might look like. So with that, we finished step 2. We built the next tree based on the errors of the previous tree. So finally, the last step, step 3, is to combine the trees from step 1 with the trees from step 2. So here, this is our root node from step 1. And this one here is the tree from step 2. That is our step 2 tree, and now we combine the two. So every time we make a prediction now, we use both trees and combine both predictions into one prediction by adding them. So it's an additive model. So gradient boosting can be considered as an additive model. So let's take a look at a concrete example, Lansing. Let's say we now have a data point like this Lansing data point and we want to make a prediction for this one. We first we use all the trees sequentially. So here we only have 2 trees because we only did step 1 and then step 2, but we didn't repeat step 2. So we have the step 1 root node, which is always used. And the prediction would be 0.5875. And then to this prediction we add the prediction from the second tree, from step 2. So for the Lansing tree we have an age smaller than 30, so it goes here. And then we check the number of rooms. The number of rooms is actually smaller than 10, so we go here. So for Lansing we are at this node if we make a prediction for Lansing. And like we said before, if there are more than one target variable at a given node, we average. So the prediction from the second node for Lansing is minus 0.4125. And then we combine the two. So we have 0.5875 plus the minus 0.4125. And in practice, let me delete that because I just see I actually wrote this at the bottom here. So in practice, we also use an alpha value here. So when we combine the two predictions, this is from the root node and this is from the step 2 tree, we also use an alpha value here, which is, you can think of it as a learning rate. If you recall from Statistics 453 how we use learning rates in gradient descent, you can think of it as a learning rate, or let's say it's a step size. And we usually set the learning rate between 0 and 1. So ideally we would set it to 1, then we would have the best prediction here, right, on this data set if we would set it to 1. Because for example, if we would set alpha to 1, 0.5875 minus 0.4125. So let me write this here. So for alpha 1 we get the prediction of, I think it's 0.175, which is actually not too far off from the target value, right? If I would set, the alpha value is smaller, let's say 0.01, then the difference, so it would be more dominated by the root node, and in this case it would be closer to, I think, 0.55 approximately. So in this case, the larger the alpha value, the more, I would say, correct the prediction would be on this particular data set, training data set, but that could lead to overfitting. And if I go back a few slides, so we usually repeat step 2 multiple times. So we go back after this step, we go back to 2 and then fit another tree on the errors of the combined tree and so forth. So we usually do this many rounds, and we usually want to build up slowly, like with a small step size, and that is usually better for preventing overfitting. So we usually add more trees here by learning from the residuals of this prediction, for example. So you would basically have another column like that, but based on the predictions from these two models, and you would continue going on and fitting trees until you reach a set number of trees. The number of trees can be, for example, set based on a hyperparameter setting. And that is essentially how gradient boosting works. So you start with a very simple tree, the root node, make a prediction, and then based on the errors of the root node, you compute these residuals, and then you fit another tree on the residuals, and then for the prediction you combine the root node with this second tree to make predictions, but then you can compute again the residuals from the combined tree and fit a third tree on, and so forth, and then you can keep repeating that procedure until you reach a desired number of trees. And here's a general overview of the gradient boosting algorithm that is more like agnostic, so that would be something we can use for both regression and classification. So we start with the input dataset, our training dataset. We use also a differentiable loss function, for example, the mean squared error in regression or the negative log likelihood in logistic regression. And then in step 1, in the first step, we initialize the model as the root node. So H0, that's our root node. So if our error is the mean squared error or sum squared error, either way would be fine for the regression case, then minimizing this term here, the argmin, so basically what argument would minimize this loss term, the sum of the loss for all the training data points, that would turn out to be the average. That's what we've done in the previous slides. So the average would minimize this loss basically for regression for the sum squared error or the mean squared error. And then in the second step we fit the T trees. So T is, you can think of it as the number or total number of trees or iterations. And in each iteration we compute the pseudo residual that we talked before. So before we just said simply that this is the difference between the prediction and the target label. So more formally, or let's say not more formally, but more general, in more general terms, so that it works with arbitrary differentiable loss functions. So yeah, one requirement is that this is differentiable. So then we would compute the partial derivative of the loss with respect to the predictions. And I should say, these predictions are of course the predictions from the previous round, so from round T-1, right? Because now we are fitting in the current round a tree based on the errors of the previous round, the residuals. So then we fit the tree and create the terminal nodes. And I will explain these in more detail shortly. I just want to go through the whole algorithm first before I dive into more details. So continuing now, step 2. So let me go back one more time. So here I have steps A and B, where we fit the tree to the residual values and create the terminal nodes for the current tree. So this is just repeated here. Now for the terminal nodes J, so the tree at iteration T will have J terminal nodes. So for each terminal node we now compute the prediction at that node, right? So what we would do in order to compute the prediction, we would again have a problem where we want to minimize the loss. So in the case of the mean squared error or sum squared error, we would be again computing the average at the given node. So what we are doing now is we're computing the loss between the true label again. In this case, the prediction of the previous round plus the prediction at that given node basically. So what we are computing is the loss between the true label and the predicted label, where this is the model at the previous, or let's call it previous round, or maybe previous round model, plus then the y hat term, the prediction at this current round. That's the one that we want to get right, which could be the current round. This could be the average at the given node. If we talk about the regression case, so here again this is minimization problem. So now once we have determined our prediction for each node j, we can then compute the current model by combining the previous model plus this new prediction step here, weighted by the learning rate or step size. So this term here, it looks maybe a little bit more complicated than it should be. This is just a way of adding the new predictions to the current predictions. It looks a little bit weird. It's the indicator function here for all the features at the given node, but what that essentially means is we are adding the new predictions to the old predictions, so to make the new model. So and then once we have our model updated, we would repeat this step until we reach t, until we have t models. So again, then we would walk through steps A, B, C, and D, where step A was computing the pseudo-residual, where now this term is the model from the previous round. So we are computing the derivative of the loss, for example, the mean squared error, based on the true label, and the current model with respect to the model predictions. So this is these are the predictions. So we are computing the derivative of the loss with respect to the predictions of the previous round's model. Then when we computed the residuals, we fit again our tree, determine the prediction value that then minimizes our loss based on the current node, and then update the model again, and we would keep going until we reach, or until we have done that t times. So and the differentiable loss function, that could be, if you think of logistic regression as a classifier where we use the negative log likelihood loss, this could be also the negative log likelihood here for classification. However, we haven't talked about the negative log likelihood or cross entropy yet in this class, so this is a topic in set 453, so you don't have to know this for this class. So in this case, we are just thinking of the sum squared error or mean squared error here, and then if we would compute the partial derivative of this loss function with respect to the prediction, that's actually pretty straightforward. You've probably done that when you learned about gradient descent at some point. So if we have the sum squared error here, sum squared error, by the way, this is equivalent for the mean squared error. So here we only have one data point, right? So there's no mean really, and also no sum really. So it's just a squared, just think of it as a squared error term here. But this would of course also apply if we would insert 1 over n here with a sum over the i's, right? Or so if we have the 1 over n here, then this would be the mean squared error, and if I would drop the 1 over n, it would be the sum squared error. Technically what I have here, the SSE, is just the squared error because I don't have a sum over the training examples, but the same concept applies. The 1/2 is just something people use in practice, so it cancels. So I can then differentiate that using the chain rule, like inner times the outer derivative, right? So we have the inner term and the outer term is the power here. So we are applying the chain rule now when we want to compute the partial derivative of this loss with respect to the prediction. Let's do the outer first. For the outer one, we can, using the power rule, right, bring this one here. So that's 2 times 1/2. So this cancels, this is just 1, right? And the inner derivative, this one is obviously 0 because we're looking at the partial derivative with respect to the prediction. So this term is a constant, so it will be 0. And this part will be 1, right? What we have then here is the outer derivative times the inner derivative, and this gives us this term here, which is the negative residual that we talked about when we walked through the example for gradient boosting. So, but this is like for the sum squared error case, but this is an arbitrary concept. You can, use any type of loss function here as long as it's differentiable. So what else do we have here to discuss? So yeah, again, like I talked about before in step 1 when we talked about this minimization step here. So this term here, this expression here, is minimum if we just use the average in regression. So if we compute the average at a given node, we minimize this term. So we find the prediction that minimizes this expression here, that minimizes the loss for all the training examples at that given node, where y hat is the predicted target, and this is the ground truth target, or just the true label. So the loss is minimized if we just compute the average in the case of the sum squared error. Then in step 2 we talked about t, so we have a loop here for t trees that can be a hyperparameter that you would set when you run gradient boosting. This term here is the pseudo residual of the tth tree in the tth round and the ith training example. So you compute that for each training example, of course, like we've seen in the table. Yeah, and then we have the n training examples for which we compute the residuals. Then we fit the tree to these residuals, creating the terminal nodes. So t stands just for the t in the tth round here, and j is just the indicator for the node. So for example, if we have 3 nodes, we would just numerate them, R1, R2, and R3. Yeah, then we compute the prediction at each leaf node. I should have probably written prediction here, where we only consider the examples at each node. So at each node, we compute the prediction separately, right? So this is basically just the averaging. So here and here there is no averaging, but here we have to compute the average, right? So that's what we're doing here. So for each node, j1 to jt, we compute the prediction, which is again the averaging here, right? This is the minimization term. In sum squared error, it turns out if we compute the average, this would minimize this loss term. But now here the difference is that it's a loss between the target label and the previous tree's prediction plus this current term that we want to find, basically. It's essentially similar to step 1 when we go back. If I go back to step 1, it's similar to this term here where we compute the average, except that we now have the previous model added here, right? Yeah, and then we update the model by adding this new term here. So this is a new term with a learning rate between 0 and 1. Yeah, and then depending on the implementation, if we have a case where an example ends up in multiple nodes, then we also have a summation term here. Yeah, and then after we are done, we are combining all the predictions. So these terms are usually found by minimizing this loss function here, right? That's what we talked about. So in practice, when we have t trees, we would combine all of these. So in each round we have a different type of prediction because it's depending on the residuals of the previous tree, and every one has a learning rate. Usually the learning rate is the same for all the trees. You can think of it maybe improving it by using a learning rate scheduler like we do in deep learning, but in practice, usually people use the same learning rate for each step. And then we are adding just up the predictions for each tree. Yeah, and the idea behind the learning rate is that we decrease the pseudo residuals by a small amount at each step to basically avoid overfitting. Phew, we covered a lot of ground discussing gradient boosting, and I fear it's going to be another long video scratching the 1 hour mark. I don't want to make it too long, but there are a few more interesting aspects about gradient boosting that I want to discuss, and that is mainly related to how we use gradient boosting in practice nowadays. So gradient boosting is a nice, great algorithm. We've seen that it makes sense. It seems to be quite a good idea to do this kind of boosting. However, one downside with boosting is that it's a sequential algorithm, and the problem with sequential algorithms is that they are usually pretty expensive because we can't parallelize these, so we can't take advantage of multiple processors or multiple computing nodes when we fit the algorithm, which can be one downside. And then also, if you think back of the efficiency of decision trees, when we discussed that, one expensive aspect about fitting decision trees is if we have continuous features and we want to find a good splitting point. So we have to evaluate all the features in also each feature column, but then also for the continuous feature column, we also have to find a good splitting point. So evaluating different splitting points, and then for each of them computing the information gain, and that can quickly add up, making not only the decision tree expensive, but then think about having a sequence of decision trees, so it's even more expensive then. So gradient boosting is not a cheap algorithm computation wise. However, Chen and Guestrin, they proposed implementation of gradient boosting that is more efficient, and this implementation is called XGBoost. So in XGBoost they used several tricks to make gradient boosting more efficient. So this paper came out in 2016, but I think XGBoost was there earlier. I don't remember exactly which year. It may have been 2013, 14, 15, something like that. And as they describe here in this passage from the paper that I copied, what they say is, it's actually a weird line break, what they say is among the 29 challenge winning solutions published at Kagel's blog during 2015, 17 solutions used XGBoost. So 17 out of 29 Kaggle solutions used XGBoost, and these were actually the winning solutions, which is quite impressive. So more than half of the Kaggle's winning solutions used XGBoost actually. So just to provide a little bit more detail, among these solutions, 8 solely used XGBoost to train the model, while most others out of the remaining 8 combined XGBoost with neural networks in ensembles. So for that, you can, for example, think of the ensemble vote classifier that we talked about. You can maybe also, use bagging for that to combine multiple XGBoost classifiers. But then one popular technique that I see often used is using stacking, which is another ensemble technique. So stacking is somewhat similar to ensemble voting, except that we have one more classifier that combines the predictions of the previous classifiers. And we will talk about that also in this lecture. So if this sounds weird what stacking is doing, we will revisit that in lecture 7 here. After this video we will talk about random forests and then about stacking. So just be a little bit patient, we will discuss stacking too. This is just highlighting XGBoost is a really useful practical solution, and it led to many winning solutions on Kaggle. So it's performance-wise, in terms of predictive performance at least, a pretty good approach for getting good accuracy on prediction tasks. So here are 2 tables from the paper that I found quite interesting, table 1 and table 3. So table 1 compares the major boosting implementations in open source software. So there are different software libraries implementing gradient boosting. So the XGBoost library also comes with certain improvements, and the different columns list the different features of the XGBoost implementation compared to some other implementations. For example, here's the R gradient boosting machine. There's a scikit-learn implementation. Actually, there's a newer scikit-learn implementation now, a second one that we will talk about also briefly in this video after we finish the short discussion on XGBoost here. And there are some other libraries like HDO, Spark. Actually, I don't know what this one is. But in the columns, they compare the features of these different implementations. So XGBoost implements certain additional features. Exact greedy is not one of the unique features about XGBoost, because that's something that also the classic gradient boosting has. So it's in XGBoost, but also in scikit-learn and the R implementation of gradient boosting. And the paper calls exact greedy the method of considering all the possible splits of a continuous feature that we also talked about in card. So it's not, I mean, they say it's all possible splits, but it's technically not all possible splitting thresholds. It's just all the different ways you can split a feature, such that the class labels are different. So for simplicity, you can just think of it as the regular way we use card, and it's also how you implement card in the homework when you use the get threshold function and the get best threshold function. So it's basically like the get threshold, and the get best threshold functions in the homework. The other feature is the approximate global here. So the approximate global, this is like an approximation that is, I think, used, when I remember correctly, if the data is split across different computing nodes. So you can run XGBoost on different computing nodes. And then the data, so the point is, if you have a very large data set and you can't fit it on one computer, you can distribute your data set across different computers, but then every computer has only a subset of the data. So how do you find the best split based on all these subsets? So also to make it fast, what this approximate method is doing is it's computing some summary statistics from each dataset subset, and then based on these summary statistics, it's approximating a good split. So it's like an approximation, and it can also do this approximation locally. Yeah, it also supports out-of-core learning. Out-of-core means that we don't have to have the whole dataset in the memory. If the dataset is large, it supports having them on disk. So at least that's what out-of-core usually means. Then it's also sparsity aware. So sparsity aware here means that it can deal with missing feature values. So it also implements some imputation techniques for imputing missing features, which is nice in practice. So that's not really improving the computational performance, but it can improve the predictive performance, because then we don't have to drop these feature columns. And yeah, lastly, it can also be run in parallel. So there are, due to these approximations also, the execution is parallel or can be parallelized, which is nice. So in this table 1 was summarizing the features of XGBoost. And table 3 compares the performance of different gradient boosting implementations using the exact greedy method on the Higgs 1M dataset, which is a relatively large dataset. And each gradient boosting machine is fit with 500 trees. And yeah, what you can see is here, if you look at XGBoost and the scikit-learn one, they have basically identical performance, which is nice. But yeah, this is also the exact greedy method, so it's kind of expected that the performance is the same as for the original gradient boosting, because this is the exact one, not the approximate one. But then what's notable is that you can see that the time per tree is significantly reduced. So you can see it's 0.68 seconds per tree instead of 28 seconds per tree. And you can think of, if you have 500 trees times 28 seconds for the scikit-learn one, so that would be pretty expensive and a long time to wait. And then if you also consider tuning hyperparameters, so there are some hyperparameters to tune, like the size of the tree, the learning rate and so forth, it can be pretty expensive if you have to run 500 trees and have to wait like half a minute per tree. That's 250 minutes, right? So yeah, in that way, XGBoost is pretty attractive here. So also let me clear this because it's hard to see the other values then. Oops. So what's also interesting is, I don't know exactly why, but I mean, the R implementation of GBM, gradient boosting, is also pretty fast, only 1 second per tree. But look at this, I mean, this accuracy is not really convincing. I mean, compared to this one, it's like 20% lower. Actually, I see it's AUC. AUC stands for area under the curve. And so I was saying accuracy, but AUC actually means area under the curve, which usually refers to ROC, area under the curve. And ROC stands for receiver receiver operator characteristic. We will talk about this. Oops, there's no space. Don't worry about it now. We will discuss this later in a different video when we talk about different evaluation metrics. So the receiver operating characteristic, area under the curve, is of course not the prediction accuracy. It's a little bit different, but there was a paper. There's a high correlation between accuracy and the receiver operator characteristic under the curve. So you can think of it for simplicity also as prediction accuracy. So for some reason the prediction accuracy here is 20% lower compared to XGBoost. I don't know why exactly, but that's not very nice. And yeah, interestingly, there's also another row with XGBoost. It says call sample 0.5, and if I recall correctly, this refers to using random features at each node. So call sample 0.5 means choosing a random sample of the features. 0.5 means 50%. So you select a random subset that is half the size of the original feature subset at each node. So instead of considering all the features at each node in each tree, you only consider a random subset, half of the features, differently at each node. That is similar to random forests, which is a concept we will discuss in the next video. So by that, you make it computationally cheaper, but in some cases it can also improve the generalization performance, because if you randomly select features for finding the best split, it can help with avoiding overfitting. So based on the paper, I actually highly recommend you to read the paper. It's very readable, very accessible. So I will also post this paper on Canvas. If I forget again, then please remind me. But I think you can also find this online if you just search for it in the worst case. So I highly recommend you to read that paper. It's very informative, very nicely written and easy to read. But here are some of the summary and main points from the paper. So XGBoost is essentially a scalable implementation of gradient boosting. With scalable, I mean it works well on large data sets without being too resource prohibitive. So you can even run that on large data sets in a reasonable time. And there are several improvements also to the normal gradient boosting procedure. For example, they use a regularized loss. They have like this imputation technique for dealing with missing features. They have some approximation for the tree learning. They call it weighted quantile sketch. They do some caching also, data compressing and sharding. That means also like splitting things across different machines. And yeah, these make XGBoost computationally more efficient, but also it has been shown that some of the techniques help with reducing overfitting, which can then improve the overall performance of XGBoost. Yeah, the decision trees in XGBoost generally are based on the card algorithm that we discussed before. And the regularization term I mentioned is for penalizing the model tree complexity, so it basically helps with keeping the decision trees simple to avoid overfitting. They also use second order approximation instead of just the first order stochastic gradient descent. They use a second order approximation for computing the gradients, or minimizing the loss function, I mean. Then they have options for column-based and row-based subsampling. So column-based subsampling, this is like a little bit of a jargon in machine learning. Like if you just say column and sample-based subsampling, it would be, I think, better to say what that means. That means feature-based subsampling and training example-based subsampling. So if you think of the design matrix that we usually use in machine learning. So we have n training examples. Oops, what happened here? N training examples and m features as the columns, right? So feature-based subsampling or column-based subsampling means that if you think of all the feature columns here, you only randomly select a subset of those. For example, you may select this one, this one, this one, and this one. So you have a smaller data set, fewer features. And then for each node you have a smaller subset, which can help with reducing overfitting. The row-based subsampling would be basically selecting a random subset of rows, which is somewhat related to bootstrapping that we discussed earlier. And it can also reduce overfitting. And then there are these different approximation techniques for finding the splits. But if you want, you can also just use the exact greedy algorithm, which is similar to the normal gradient boosting. So that was XGBoost in a nutshell. Lots of information in a few slides, I know, but I highly recommend you to read the paper also in addition, which is describing everything in more detail. So part of this lecture is also just to give you the taste or the overview, and of course the details are all in the paper, so I don't want to just go into the same detail as in the paper, because otherwise we would spend like 4 hours on each little topic here, and then we wouldn't make progress in this course, or not that much progress. So some of it is also like as a homework exercise, a reading exercise. Anyways, XGBoost has been around like for half a decade now, or a little bit longer even. So there are also other implementations now of gradient boosting machines. So by the way, GBM, when I say GBM, it stands for gradient boosting machine. So GB for gradient boosting and M for machine. It's like the old term. And there are also nowadays gradient boosting machines newer than XGBoost, which are even faster and apparently better. One is Light GBM by Microsoft, which has some other tricks that it implements. And here from the website, I have also some tables comparing XGBoost with Light GBM. So here that's the original XGBoost. Here's an improved version of XGBoost, and here's Light GBM. And this is the unit in seconds, like speed in seconds, I assume. And you can see on the different data sets, so they consider different data sets. You can see that the improved XGBoost version is even much faster than the original gradient boosting implementation in XGBoost. And Light GBM is even faster than that. So they are in most cases almost twice as fast as XGBoost. But then moreover, instead of just being faster, they also have a better prediction accuracy. So you can see, for example, the AUC, the area under the curve, for the receiver operating characteristic, you can see that also Light GBM performs better in almost all cases, except this one data set where, I would say they're almost tied. But overall, Light GBM is even a better alternative now, I would say, based on the speed here and based on the predictive performance. So what is this improvement of XGBoost? By the way, Light GBM also uses this aspect. It's called histogram-based split finding. So I found a nice website here that just briefly summarizes it. So they say basically both XGBoost and Light GBM support histogram-based algorithms for split finding, which is essentially bucketing a continuous feature into discrete bins. So if you have a continuous feature, you basically create a histogram out of that, and you kind of bucket this for the training example. So you have then feature intervals, and this can then be used for splitting and improve the speed during training and reduce the memory usage. But then historically they have also found that it can reduce overfitting. So you can see that this histogram-based split finding improves the performance. If you consider XGBoost without that and XGBoost with the histogram, you can see the performance is greatly reduced. Improved. It's faster now. So I should say the smaller the number, the better, right? But then also you can see that in some cases, like here, it improves the prediction performance, and I'm pretty sure that's just related to overfitting, because now with the spinning, it may not perform so well on the training set, but then when we consider a test data set, it may reduce overfitting. And both Light GBM and XGBoost support this histogram-based split finding. Light GBM has some other parameters for that than XGBoost, so here are the hyperparameters for the histogram-based split finding if you want to toy around with that in your implementation when you use it in your class projects. And so the article was from this website, which is quite helpful because it has this overview of the histogram-based related algorithms. And then lastly, a few words about Light GBM. So you can use Light GBM just directly from the GitHub repository, from Microsoft's GitHub repository. It's also free and open source software. which offers then basically better speed, lower memory usage, better accuracy, and so forth compared to XGBoost. But you saw in the previous slide the difference is not that big. So in a class project, why not even use both and compare them to each other? That might be interesting. But yeah, in addition to that, 2 versions of scikit-learn ago, they also added a new gradient boosting classifier. So originally in scikit-learn they had the gradient boosting regressor and classifier, which was great. It implemented the exact gradient boosting method that we talked about, but it was slow, as we've seen, based on the XGBoost table 3. However, based on LightGBM, they also implemented a hist gradient boosting classifier using this histogram-based splitting. So they actually say it's inspired by LightGBM. I remember seeing on Twitter that Andreas Müller, one of the scikit-learn contributors, posted some speed comparisons, and I think it was even faster than LightGBM, or at least the same speed, which was pretty impressive. So instead of even going here and using LightGBM from there, you can also just use it just from scikit-learn nowadays if you want to. But also, it might be just interesting for this class project if you consider using gradient boosting. It might be interesting to compare XGBoost, LightGBM, and this hist gradient boosting classifier, just to see whether they really perform equally well. But yeah, that was like the brief overview of gradient boosting or modern gradient boosting in practice. And lastly, I want to show you some code examples that you can use as templates for your class projects or otherwise. Yeah, let's get started by looking at the simplest case first, which is the gradient boosting classifier implemented in scikit-learn, which implements the basic gradient boosting procedure. So here, this code chunk, or this notebook cell that I screenshotted here, is just copied over from the previous videos when we talked about AdaBoost and bagging and the Ensemble vote classifier. It's just loading the iris data set. I know iris is not exciting, but at least this is short and gets out of the way, so we don't have to discuss the dataset and can focus on the few lines of code about the classifier. And also note that we are only working again with 2 features, the sepal length and the petal width, to keep it rather simple. Otherwise it would be too easy to get 100% accuracy all of the time. So here we are just keeping it simpler. And then we are implementing the gradient boosting classifier from scikit-learn's Ensemble submodule. So except for the random seed here, these are the hyperparameters that I was defining. So these would be hyperparameters to tune, for example, via grid search or randomized search and so forth. I think the learning rate I kept the default, and the number of estimators, these are both default values. I only changed the max depth for the decision trees in the gradient boosting classifier. I think the default was 3, I changed it to 8, because I think 8 or 32 are more common values that I've seen in practice, but of course it's a hyperparameter and really depends on the problem at hand. So I didn't do any hyperparameter tuning here, so that's why I am not using a validation dataset. I was just defining this and running this, and I got a 95% accuracy on this test set here. And the second classifier here is the newer one, the hist gradient boosting classifier in scikit-learn that was added, I think, in scikit-learn 0.21, so version 21 in scikit-learn. And by default, when you try to import it, you would get an error message. So what you have to do is you have to add this line here in order to use it, because it's still considered experimental. So if you import enable hist gradient boosting, this experimental procedure, you will be able to import it. Here, the way we use it is the same. We define or initialize the object, the hist gradient boosting classifier object, so an estimator object here. It doesn't have an n estimator parameter, at least I haven't seen it. So I think it's computing a good number of estimators automatically, like having a stopping criterion. And the way we use it is the same way, like we use every estimator in scikit-learn. We have a fit method, and then after that we can call predict, or we can use the score method to compute the accuracy. So here in this case we get a 97% accuracy. Thirdly, here is code for using XGBoost. I recommend actually going to the website of XGBoost, which gives some recommendations for installing it. I just pip installed it here, but for different operating systems there are different recommendations. So I really recommend going to the website to find out how to install it in a way that is good for your system. It's a little bit, I would say it's very similar to scikit-learn, but it's a little bit more, I would say, involved than just using scikit-learn, or it's a little bit different. The API is a little bit different. So you first have to convert the NumPy arrays into their own dmatrix format. So also here, this is for NumPy arrays, this command here. There are different commands if you want to load data from an SQLite file or a CSV file and so forth. So also for that, I recommend checking the documentation if you want to use XGBoost. And then we define the parameters in a dictionary here. So again, I'm setting the max depth to 8. It's just something I set arbitrarily. Again, I didn't do any tuning here. I set the learning rate, it's called eta here, to 0.1. Then using a multi-classifier. Then using a multi-class classification loss here. And then we also have to specify the number of classes in our dataset. Yeah, and instead of using the fit method in scikit-learn, in XGBoost we use .train, which is equivalent, except that we have to provide the parameters, or the parameter dictionary is the first parameter, then the training set, which we have here. So it contains both the features and the labels. And then we specify the number of rounds during boosting, so the number of estimators. And after we've done that, we can call predict. So if we call predict, it will return a matrix which has the different columns for the class membership probabilities. So here, using the argmax, like we've discussed in the earlier lectures, I'm converting the probabilities, the class membership probabilities, to class labels here. So these are I should have called it maybe Y labels predicted or something like that. These are actually the predicted labels, but I think it's obvious if we have a short code example like that and look at it. And then we are computing the accuracy. So XGB, I don't think it has a score method, or maybe it has, I just didn't try. So here I'm computing the accuracy, so I'm just checking how many of the predicted labels equal the labels in the test data set, and then averaging it, so that gives me the accuracy. So here in this case I also have a 97% prediction accuracy. Lastly, Microsoft's Lite gradient boosting machine, Lite GBM. So again, I recommend you to visit the official website for installation instructions. It might be different for different operating systems and so forth. I was using Conda Forge or Conda from the Conda Forge in a repository to install Lite GBM. And after installing it, we can import it, and it follows API similar to scikit-learn, which is nice. So we can initialize the LGBM classifier object, and then we set our hyperparameters like similar to scikit-learn, and then we fit the gradient boosting machine, and then we can use the score method to compute the accuracy. In this case, it's actually quite impressive given that I didn't tune any hyperparameters, so it gets 100% training accuracy. Okay, that was a very long video. So in the next video we will be talking about random forests, which are a little bit simpler, and it will be a shorter video for sure. And then after that we will talk about stacking, which will hopefully be also a shorter video. And then we will have wrapped up lecture 7 and go on to model evaluation.